Okay, Assalamu alaikum. This is basically the past paper class for deformation. So we are going to start up some theory papers. The question states that a spring is suspended. Well, we can see that for the spring state, the name of the law that gives the relationship. So quite obvious, we can just write Hooke's law. It says determine the spring constant in Newton meter. Okay, so we have Newton and we have centimeter. So we have to find out the spring constant. That would be F over X. So if we find out the force here, that's going to be 12, and the extension here is basically not 24 because it starts at 8. So the extension here would be 24 minus 8, and that is going to be 16 centimeters, which is going to be 0.16 meters, right? So 0.16. So 12 over 0.16 is going to be 75 Newton meter. Part C says determine the elastic potential energy when force is 6 Newton. So here we go. If we see that force is 6 Newtons, that's here. And this goes on to an extension of 16. Well, so from 8 to 16, that's 8 centimeters. And this is basically 6 Newton. So elastic potential energy, or EPE, we have done, there are various formulas for it. You can use half area under this curve or half kx squared. I'm going to be more comfortable with this. I just figured out basically k, or either way, it's the same thing. You don't have to worry about that. So let's do half k and x squared. So that is going to be 8 over 100 squared. So the answer I have is 0.24 joules. So the next question is question 2. They say a rigid uniform beam, blah, blah, blah. We can see this here. So we have a beam. Okay, well, show that the vertical component of the tension in the string is 2.4 Newton. So that's the string here. Vertical component. So let's resolve it. This is going to be the horizontal component. That is going to be the vertical component. So vertical component, horizontal is cos component and vertical is sine component. So the vertical component would be T sine 30. So tension is 4.8. Sine 30 is basically 0.5. So half of 4.8 is going to be 2.4 Newton. By taking moments about the hinge. So do we have a hinge here? Yeah, we have a hinge here. Okay, determine the weight of the beam. So we have to find out this. So using principle of moments, which states that clockwise moments should be equals to anti-clockwise moments. Well, they are interested in the working as well. So you have to find out clockwise and anti-clockwise moments. So first thing is this is going to be the perpendicular component of tension, and the hinge is here. So that's going to be basically clockwise. This is still clockwise. This is still clockwise. So anything that's anti-clockwise. So for hinge, we don't have anything that's anti-clockwise, right? So they would be basically equal to, well, yeah, that's nice. That's this part of. So we have a spring here. So once this is obstructed from this side, this is compressed. So the spring force acts like this. That is going to be, anti-clockwise, right? Because once you put some weight on this beam, this is going to be pushed downwards. That compresses the spring. So the spring should exert some force, right? So that's the spring force. Yeah, that's nice. So that is going to be the anti-clockwise force. So that would be F times 0.50, and all of the others are clockwise. So W times the distance from the hinge. So zero point 0.5 plus zero point 0.1, that is basically zero point 0.6. That is very important. This is the distance for W, right? And then we have a weight of zero point 0.3 Newton, which is even farther away than the original distance of zero point 0.6. So zero point 0.2 plus zero point 0.1 plus zero point 0.5. So let's add this up. So 0.30 times zero point 0.2, zero point 0.1, and zero point 0.5. So that's going to be zero point 0.8, right? And then we have the vertical component, that's 2.4. We just figured that out. And then the total distance, so zero point 0.8 plus zero point 0.4 is that. So that's 1.2, right? So 1.2. Now, what's the spring's force? So the question says a compressed spring exerts a total force of 8.2 Newton. Well, that's given. Now it becomes very easy. So you have the entire equation, you just have to solve it and find out the value of W. So substituted in the calculator, you're going to get 1.6 as the weight. Now calculate the horizontal component of the force exerted on the beam by the hinge. So the only horizontal force you have here is this, right? So basically hinge should exert an horizontal force in this direction since it is in equilibrium. So if it is in equilibrium, total left, total right should be equal. So that's cos 30. So that would be horizontal component T cos 30 as the resultant force. So that would be 4.8 cos 30. So 4.8 cos 30 gives me 4.2 Newton. So that's the force here. Hope that clarifies things here. Then they say this spring obeys Hooke's law and has an elastic potential energy of 0.32 joules. Find out the compression of the spring. So, well, we have the elastic potential energy. So we have the force. We don't have a spring constant here, right? So we can use half Fx. We don't have a spring constant, so we can use this, right? So we have elastic potential energy, that's 0.32 joules, that's zero point 0.5. Force is just what we have figured already out. It is given in the question, that is 8.2, and x is unknown. So let's find out x here. So that would be basically 0.078 meters, right? I hope that clarifies things. Let's see what's next. So, well, we have another question here. It says that define the Young's modulus. So Young's modulus basically is the ratio of stress and strain. So the ratio of stress and strain is going to be the Young's modulus. Ratio of stress and strain, uniform wire, suspended, blah, blah, blah. Okay, we can see that. So let's see what they ask us later on. Okay, so we can see that there is a wire support masses and they say find out the cross-sectional area of the wire is 0.95. Okay, determine the unstretched length. So we have force and we have length starting here. So unstretched length would be when force is zero. So force is zero, the unstretched length is basically given. So there is nothing to worry here. So that would be 1.998 meters, right? Yeah. So for an applied force of 30 Newton, well, now here 30 Newton, determine the stress. That's force per unit area. So force is 30 Newton. Area was given in the question, that is 0.95. And from square millimeters to square meters would be exponent minus 6. So 30 over 0.95 is going to be 3.2 exponent 7 Newton per meter square, or pascals already there. It's strain of the wire. So strain is basically change in length over original length. So that would be basically x upon L or E upon L or whatever you do, like delta x over x, whatever you like to have. So change in length. So from here to here, wire is stretched. So the change would be 2.003 minus 1.998. So the answer comes out to be 0.0050. And the original length is already here. So that would be 0.0050 over 1.998. 1.998. So we have what? 2.5 exponent minus 3 with no units. See, 3 marks for this much easier part. That's nice. That's a simple question. So we have another question, question four. It says this horizontal spring is fixed. Okay, it is now compressed and it is released with a speed of 2.3. There is a mass of 250 grams and a spring constant given. Calculate the kinetic energy. So such an easier question that would be half mv squared. Mass is already there, that's 0.250, and V is given in the question 2.3 squared, so we are going to get 0.66 joules. Okay. Now, calculate the compression of the spring immediately before the block is released. Okay, so we have to find this compression. So say we have a spring constant and we have the EPE. So that's basically, the kinetic energy here is basically because of the elastic potential energy stored in the spring. So if you apply law of conservation of energy, we can just write that kinetic energy is basically due to EPE, right? So EPE is going to be 0.66 joules. And then if you use this formula, EPE would be half kx squared, right? The elastic potential energy is 0.66. Half k is already given in the question. That's 420. Okay, so x is going to be 0.66 times 2 over 420 within a square root. So what do I have x? Well, it comes out to be 0.056 meters. Okay, was an easy question. It says after leaving the block, okay, change in momentum I have to find out. That means I'm looking for velocities. So after leaving the block moves along the surface until it hits a barrier with a speed. Okay, that's then the speed and then it rebounds. Okay, so we have to change the direction. Okay. So momentum is basically m delta v. So mass is already given in the question. That was 250. So that becomes 0.25. And then basically velocity, if let's say we take, for example, 2.3 as positive. So minus 1.5, right? So if we do, let's say that's initial and then that's final, so it becomes V minus U. So for the change in momentum, right? So that would be minus 1.5 and minus 2.3, right? So regardless, the velocities are going to be added. So the momentum change would be 0.95 seconds. The understanding is if I'm having a negative sign in change in momentum, that means the resultant momentum is basically not towards the right hand side, it is basically towards the left hand side. Not towards the left hand side, basically towards the right hand side, because I assumed right to be positive, right? So my answer shows that this has to be designated towards the left side. So either way, it's the same thing. No worries in that. If a candidate ends up with, something like this being negative and this being positive, so he can get the answer as positive as well. So not of an issue. Now the examiner's favorite choice always after change in momentum, they have to go towards resultant force. Well, now, buddy, we know already this. That's Newton's second law. So we can do 0.95 over time. Time should be there. So the block is in contact, see, 0.086. So we divide it. We are going to get 11 Newton as the answer. Now, this say the maximum compression X is now varied in order to vary the kinetic energy. Okay, that means we are studying the relationship of compression. So the idea here is that if we have, more compression, if we have uh, larger compression. So basically, we are going to have more kinetic energy. So the relationship is going to be direct. But thing is, if we understand the equation of kinetic energy that is converted here in the elastic potential energy. So that's related to square of the compression. So that's not a linear relationship, but a squared relationship. So what we expect is a curve and as basically X increases, kinetic energy should increase because that is representing the elastic potential energy. So it has to be a curve and it has to increase because the quantities are basically kind of increasing each other. So it has to be something like this. right? So we have another question, question 5. It says a steel ball is projected horizontally. So this is the horizontal velocity, okay. And when it falls off, we have distance here. Calculate the time taken for the ball to reach the ground. So if we consider horizontal part of the motion, so basically horizontal motion has zero acceleration. So the equation we can use is equals to Vt. We have S, that's basically 180 centimeters. So that is going to be basically 180 divided by 100 in meters. Horizontal velocity is already there, 4.9, and T is unknown. So T is going to be basically 0.37 seconds. Okay, so that was simple. Calculate the vertical component of the velocity of the ball as it hits the ground. Okay, so it hits the ground. That means this was 4.9 and this falls here at a distance of 180 centimeters. So they want us to find out the vertical component here. Okay, so that's what they're interested in. So basically, this is a downward motion. So acceleration is positive 9.81. That's what we are assuming. It is started from rest because here there is no vertical velocity component. So don't confuse 4.9 with the 0. 4.9 is the horizontal component, not the vertical component. The vertical component is 0 basically. Right now we are only considering the vertical part of the motion. So that's 0 and it goes all the way down. So V is unknown and we have time. We just calculated time and that was around, I think, 0.37 seconds. So we can use V is equals to U plus 80. U is 0, A is 9.81, and T is 0.37 seconds. So 9.81 times 0.37 seconds, we have 3.6 meters per second. Then they say determine the magnitude. Okay, magnitude of the velocity. So basically, the resultant velocity would be total horizontal and total vertical. So total horizontal stays same, so there is no change, 4.9 squared. Vertical is just we have calculated that's 3.6 squared. So we figured this out. What we are going to have, we are going to have a 6.1 meters per second. And then theta would be equals to tangent inverse of vertical component over horizontal component as this is the vertical velocity and that's the triangle we are expecting. So that's Vx and that's Vy, right? So basically, if say this is the angle under consideration, so that's basically opposite and that's basically adjacent. So no, that's not the angle under consideration. That's the angle under consideration. Yeah. Theta. So that's basically adjacent and that's basically opposite. So tan theta is opposite over adjacent. So that's what we have to find out. Theta tan inverse of Vy over Vx. Vy is basically 3.6 and Vx is 4.9. So we figure out theta. That is going to be 36 degrees. Okay, then we have part B here. Well, this is a ball is projected by means of a spring. Okay, we can see that. So initial compression. So the then pulled back. Okay, so the compression is X naught. Okay. Then we have compression and we have force. That is shown through a graph. Okay. Let's see what they have asked us. The ball is of uniform pair of diameter, okay, and mass this density. So density is basically mass per unit volume. That's 0.017 and volume of a sphere is 4 upon 3 pi r cubed. So half of diameter and then cubing it. So that is going to give us the density. That's the answer to density, 7,900 kilograms per cubic meter. I was more thinking like they're going to say upthrust. Okay, so all of the elastic potential energy is converted. So whether it's the similar question, we have just completed this type of a question. So we have the speed and we have to show that the maximum elastic potential energy. So we can just use the equation for kinetic energy, that's half mv squared. So they've already told us the mass that was 0.017, and then they have shown given us the speed that's 4.9, so 4.9 squared. So if we work this out, so this is going to give us 0.20 joules. So then they say determine the spin constant K. So that's the elastic potential energy. And the elastic potential energy is basically calculated through, okay, they want us to use that law. Yeah, let's use this. So the gradient is going to give me the spring constant. Let's see, what do I have here? So that's K is equals to F over X. Okay, buddy. So this is going to be somewhat here. So, well, that's not 6. That is going to be 6.2, 6.4, because that's 7, right? Yeah, so 6.4 and x. X is 10 centimeters, which is going to be 0.1. So this is going to give us 64 Newton meter. That's K. That was the question here. Then what else? They say, yeah, use your answer. Okay. See, compression. So now we can do that. E is equals to half kx squared. E is the same as elastic potential energy or the kinetic energy. We just figured out K, that was 64, and X is unknown. So let's see X. So X comes out to be here 0.079 once you solve for it. So the steel ball is replaced by a polystyrene ball of same diameter. Okay. The spring is given compression and then release. Air resistance is not negligible. Okay. Why this ball leaves the spring with a greater speed than that of the steel ball? Achha, okay. So the understanding is very simple. Since they do have the same spring, right? So they do have the same kinetic energy. So basically, if you decrease mass, say this is for steel and that's for polystyrene. So say that was 0.20, this is still going to be 0.20 because the spring is same, right? Spring is same. So that's the elastic potential energy. So if basically you're decreasing mass, so you have to basically kind of square, increase the velocity, and that's for polystyrene. So it has to lead. So that's what they're looking for here. So we can just write, since two statements are needed, since same elastic potential energy. So for lesser mass, polystyrene will have a greater speed. And don't worry about, just going out of there. So doesn't matter. Why this ball takes a longer time to reach the ground than the steel ball? So it takes longer time. Okay. So since basically here, this component of polystyrene would be a bit less. Reason being, it has lesser weight and basically air resistance is there. Hmm. So it will reach terminal velocity faster. That means it will have lesser vertical component of acceleration as compared to the steel body. So essentially, we know that heavier objects of same size and diameter as compared to lighter objects of same size and diameter, they fall quickly. Heavier objects fall quickly. Reason being, they basically reach terminal velocity a bit late since we have a larger weight, so there is more time that's needed. So they have a very high value of acceleration for heavier objects, but that is not the same for basically the lighter objects. So lighter object is going to reach terminal velocity way more quickly than the heavier objects. So that's what I'm going to write here. So reaches terminal velocity quickly, and that decreases the vertical acceleration, right? So that's going to be the case here. So we have question 6 then. A spring is suspended from a fixed point at one end. Okay, we can see that. So there is some extension happening here. We have a graph, force and length. So length basically here represents the total length since it covers the length even when this force is zero. Okay. So we have to find out the extension. Okay. Then what else? So they say determine the spring constant of the spring K. So we have basically the graph here, that's F over L. So K is going to be F over X. So force is basically say 30, and the change in length from 20 to 60. 20 to 60 is going to be basically 40, right? So 0.40. So that could be 75 Newton meter inverse. Okay, let's see what's next. It says determine the elastic potential energy, okay, for 15 Newton. Elastic potential energy for a force of 15 Newton. So if we say the force of 15 Newton is going to exactly lie here in the mid, that would be somewhere here, 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 yes. So this gives us 40. Okay, so elastic potential energy is half kx squared. We just ended up finding k that was around 75, and extension here from 20 to 40 is going to be 20 over 100. That's 0.2 squared. So elastic potential energy here would basically be 1.5 joules. That was question 6, I think. Yeah. So then we have question 7. It says a uniformity bar, initially X, Y, and Z, shaded area. Bar is now stretched. So there is a force that is applied and it has now become longer. Cross-sectional area has somewhat stayed same. So that's Z, that's the final length. Okay, what do they want us to do? Determine the expression in terms of sum or all of, okay. So the stress, the strain, and the Young's modulus. So it would be better if we keep it here. So to find out stress, that's force per unit area. So if that's the force, so the area we are looking for is the cross-sectional area. So that is going to be length times breadth. So that's the stress. Strain is change in length. So the force is applied in this direction. So it has become longer in this direction. So that's change in length, final length minus initial length over original length. And then Young's modulus, E, that is stress over strain. So that's Z minus W over Z. So that would be F over XY multiplied by Z over Z minus W. So FZ over XY into Z minus W is going to be the Young's modulus. So Z minus W over W, I'm sorry, not Z, yeah, that's the error here because that has to be change in length, right? So yeah, so the change in length is Z minus W over original length. That's not Z, that's W here. So this needs correction. That's W here, not W here. FW over XY into Z minus W. Yeah, that's the Young's modulus. Sure, okay. Then what else? So we have a copper wire that is expressed. Okay, so maximum extension zero to base Hooke's law. So it looks like it goes straight till here, and then it becomes to curve, maybe a bit here. So what would that be? So say if that's 2, so that's 3. So 2.2, 2.4. So any answer, 2.2, 2.4, I think should work. So 2.2 is what I would suggest because it looks like a curve here. So 2.2, 2.3, 2.4, whatever you want to say, that would be acceptable directly in millimeters. So yeah, millimeters. Determine the strain energy in the wire when the tensile force is 120 Newton. So 120 Newton, okay. So that's 80, that's 160. So 120 Newton would be somewhere here. So 80, say 90, and 100, and that's would be 170 here. Yeah, looks fine. So that's like what? So that should be 1 here. So 1, 2, 3, 4, 5. That's 1. So that's 1.2 and then 1.4. So this is 1.4 basically. So half kx is squared. So k is it given? No, it's not given. Yeah. So let's do half fx. So we have force, that's 120 Newton, and let's half and then x. The extension is around 1.4, so millimeters, so exponent minus 3. So the energy comes out to be 0.084 joules, right? That's the energy we have here.